Hi, Warren.
Adnan, thanks so much for having me on your podcast.
My pleasure. Today, my guest is Warren Powell. He's a professor emeritus at Princeton University, where he taught for 39 years and is currently the chief analytics officer at Optimal Dynamics. He's the founder and director of Castle Labs, which spans contributions to models and algorithms in stochastic optimization with applications to energy systems, transportation, health, e-commerce, and the laboratory sciences. He has pioneered the use of approximate dynamic programming for high-dimension applications and the knowledge gradient for active learning problems. His recent work has focused on developing a unified framework for the sequential decision problems under uncertainty, spanning active learning to a wide range of dynamic resource allocation problems. He has authored books on approximate dynamic programming and optimal learning, and he has a new book coming entitled Reinforcement Learning and Stochastic Optimization, a Unified Framework for Sequential Decisions. Warren is an Informs Fellow and a recipient of numerous prizes, including the prestigious Robert Herman Lifetime Achievement Award in Transportation Science. Warren, you are one of the most influential OR figures from the last 30 to 40 years, and it's a great honor to have you here. Thank you so much.
Really enjoyed being on your podcast. Looking forward to it.
Great. I know you've been living in New Jersey for a long time, but where do you actually come from?
So I was born in Baltimore, grew up in the northern part, went to a very nice high school, had two brothers and a sister. Three of the four of us went on to some sort of doctorate degree.
Wow.
But it's I came from a family that where neither parent graduated from college. One attended college and then got pulled off to the war.
Oh.
And but I built up from there. My mother had a very high priority on education.
Okay. I have the feeling that you seem to be a very intense person. Were you always like that?
Yes. So very young, I was very quiet, complicated upbringing. But in high school, I have to admit, I realized that I was fairly good in the classroom, and I became fairly competitive. So I think that, yes, I probably always was fairly intense.
Okay, so you think you still have this competitive nature?
I don't know about competitive. Retirement is a wonderful thing, and I have my company, but my son leads it. I'm really relaxing. I got to a level where I was able to conquer a bunch of problems, and now I'm just sort of settled into writing and explaining, and I'm just happy doing that. I don't really view that as being competitive. I'll tell you something that I also discovered in high school is I really love to teach. I love standing up in front of classrooms. My physics teacher used to let me take over his lectures. And I just love talking about what I'm doing, explaining things, helping people. That's my real passion. Competition, in high school, yes, I was very competitive. The rest of life, I've got to be honest, I was really mostly just passionate about what I was doing. I didn't sort of do it because I was going to have more of something than somebody else.
Mm-hmm. Right. What about being the one-man calculus class?
So it was a small high school. My graduating class was only 37 students. And they taught calculus, but at the correct advanced level, the kind that got you the AP credit. And for a series of years, we ended up with just one person in the calculus class. And I started off with three, and the two others just lasted a week, and they said, okay, no. I think they said they don't want to be in the same classroom with me. But fortunately, they didn't cancel the class. And it was very valuable because having that calculus class, which allowed me to place out of first year math, that's a big deal. And this was my first time seeing math at the level that I enjoyed, but it challenged me. I had to work at it. And so that was great. It was great having that experience.
Right. And what about outside school? Did you practice any sport or have any other activity?
I played soccer, but that was about it. Nothing outside of school. Growing up, I would have loved to have played baseball, but I just wasn't in a family situation that exposed me to that. So I made up for that with my son. because my son was a fabulous baseball player, and I don't think in the best of circumstances that I would ever been a standout athlete. I was okay athletically, but I'm sorry, that was skill to many, many other people who were very good at that.
Right. Well, why Princeton and why civil engineering?
Okay, so first of all, you have to understand, I had very little guidance on college, but we had somebody from Princeton come visit our high school, and so I interviewed with them. And so I said, okay, sure, I'll apply to Princeton. What did I know? And then my mother mentioned University of Virginia, and I said, okay, I'll apply there. And after applying to those two schools, I'm like, okay, I'm tired of that. I'll just do that. But let me put it this way. I had a fairly high opinion of myself. So I got into both, decided to go to Princeton. I'm not really sure why. Now, civil engineering, you have to understand, so as with many schools, Princeton would assign you an advisor right from day one. And for some reason, they chose me an advisor out of civil engineering. Now, he was actually somebody who did water resources. And he took me out to lunch, which is what freshman advisors did. And I distinctly remember we're crossing the street. Hey, how things going? How do you like physics? Physics came naturally to me. I will be honest, I liked physics. I found it came easy. Now, that was not common. Physics is usually a killer course. And then my advisor turned around and says, oh, well, you should graduate in 3 years. I suspect that he graduated from 3 years also. Mm-hmm. So I'm like, oh, okay, I guess so. So all of a sudden they said, oh, well, if you want to graduate in 3 years, you have to pick a major. And so they said, well, what do you like doing? I'm a freshman with no exposure in anything. Uh-huh. And I thought, locomotives sound cool. I like trains. So they said, oh, we have a transportation group, go up and talk to them. I went up there and I said, oh, I love the idea about locomotives. And they said, yeah, that's great, but they do that in mechanical engineering. We do planning here. And I distinctly remember going, oh, okay, planning sounds fine. I mean, what do I know? I did take one of these intro to engineering courses where they covered a variety of topics, but nothing really clicked. And all of a sudden, I was on a program to graduate in 3 years. Now, thankfully, there was a faculty member who's actually still there, but he was the one who got hold of me and says, why in the world are you graduating in 3 years? I'm like, I don't know. He said, okay, let's go back. And that was the best thing that ever happened because I was a little wet behind the ears at that time. So fortunately, we killed that off, and I took the normal 4 years. But at that point, I was now on the track of transportation. Now, you have to understand in the 1970s, a lot of people doing transportation were people who in the 60s were trying to help get the man on the moon. And in 1969, we land on the moon and all the funding went away. And suddenly a lot of people, especially from mechanical engineering, had to find something to do. So what happened was 2 people from mechanical engineering at Princeton came over to civil to start transportation, but transportation planning. Mm-hmm. So here we had these 2 ex-mechanical engineers doing transportation planning. And I'm like, okay, whatever. And we had a really nice group of people. In fact, I stayed every summer, which is how I met my wife. Uh-huh. And so I really got into it. Now, the field was very young in the 1970s. And one thing that I knew is I was a little mathematical. I liked math. I liked mathematical modeling. The math for transportation was extremely young, but it was just coming to its feet. Mm-hmm. They were starting to get some early mathematical models that were quite elegant. So that attracted me. And so I got pulled into that. I have to admit that I wasn't the only one who found the Princeton program in transportation to be, I wish it could have been a little bit more. It wasn't so much Princeton was a weakness. It was just the field at the time. Mm-hmm. But everybody says, oh, go to MIT. That's where all the great stuff is going. So I went up to MIT starting in 1977. Almost immediately found they had no clue what they were doing either. But MIT has this fabulous marketplace of courses at the graduate level. And there was one graduate student who basically saw that I was fairly bright. And he says, look, Warren, you got to go over and take these courses. Now, they were all scattered, but this was what was basically the foundation of the operations research program.
Okay. So far you didn't have any contact with OR until you went to MIT.
Well, I had one course at Princeton from a water resources guy that in hindsight, I would say that was an OR course.
Ah, okay.
Nobody identified it. It was all algorithms, and we loved it. But nobody identified it, operations research. I didn't know that there was a field. Mm-hmm. And so I get up to MIT. There I am in civil engineering, quote unquote, doing transportation. But the courses I were taking was really all the operations research courses.
Right.
Now, I knew that I liked math. I also knew that I wasn't like cut out for the math department. I never looked back and says, oh my God, I really should have been a math major. That never happened.
Mm-hmm.
I will look back in time and say, I should have been in electrical engineering doing signals. That should have been my more natural major.
Mm-hmm.
But anyway, so there I am taking these OR courses. I ended up taking exactly 3 courses from civil engineering at MIT. That was the minimum in order for me to get a degree in civil engineering. If I had taken 1 fewer course, they would have just given me a degree in engineering.
Wow.
But I ended up doing all the mathematical modeling, but in the context of transportation problems. And I have to admit, that has always been what was my passion. I like math, but I like math on a problem. I love that bridging of real problems. Now, freight transportation in the private sector was only coming to its, it barely existed because prior to 1980, freight transportation was heavily regulated. You didn't need to have a brain to run a trucking company, airline, railroad. But in 1980, long story that I won't get into, they finally got rid of regulation and suddenly you needed a brain. Now, my first 2 years, I was doing more public sector stuff. But MIT did a really great job of convincing me that I didn't want to do public sector. Okay, I got a good exposure to it and I realized, wow, that is just not a field I want to be in for a variety of complicated reasons.
Right.
By the way, one of which was no data. I mean, I'm sorry, in the 1970s, there was no data. There was nothing to do. But I was sharing an office with somebody who had landed a project with a professor who did do freight transportation, a very non-mathematical professor, but he had ties in the trucking industry, and they had landed a project that had a lot of good analytics, and I was there in the office, and they kept asking me these analytical questions, and I'm like, I love these questions. These were probability questions. This was real analytical. They were building a computer model, and they had some fairly advanced probability questions that were coming up. And every time they had something hard, they would turn to me and, I knew how to answer it. And I'm like, wow, I really like whatever problem they're working on. They have these really cool questions. So my office mate was only getting a master's. So he graduated. I went up to his advisor, says, I'd like to pick up on this project. Now, his advisor and I had almost nothing in common. But I was the one standing up going, wow, I'd like to work on this trucking project. Funded by a company called IU International. And IU International was my first company that I called as a professor, because I realized that as a grad student, I sort of waved my hands and said this had something to do with trucking. In fact, it was really just a lot of theory. So it got me a degree, it got me a prize, it got me a job at Princeton. And other than that, it was useless. But I had enough of an engineer's orientation that I called the head of this company and says, look, I know I did something that was more theoretical. I'd like to do something that's more useful. And that landed me in this path. And oddly enough, this was an industry called less than truckload trucking. My office mate ended up landing at this company called Schneider National, which is truckload trucking. So
but you were already in Princeton at that time, right? Now?
This is now very early at Princeton.
And then there was no OR in Princeton. Actually, you brought OR there in a way.
So OR has some early origins going back to the 1950s by the fellow by the name of Harold Kuhn. People in nonlinear programming know about Kuhn-Tucker and KKT conditions.
Oh, yeah, absolutely.
One of the Ks was Harold Kuhn.
Yeah.
I took linear programming at Princeton from Harold Kuhn.
Wow.
Yeah, pretty neat. Now, he retired. And now he's in the math department. So at that point, there's no operations research. And when I was graduating at MIT, I got a call from somebody who had been hired after I graduated, John Mulvey, was an OR guy. And he says, hey, Warren, we're trying to start up OR here inside civil engineering. Now, the reason for that is that civil engineering years earlier, there was a program at Princeton called Basic Engineering. And this was for students who, they wanted an engineering degree. They didn't want to be an engineer. They wanted to go into business. And civil engineering raised their hand and says, we'll host the program. And when I was there as an undergrad, I was in transportation, but there was this program called Basic Engineering. Nobody could figure out what it was. The head of it retired, and they hired John Mulvey. But John Mulvey came from operations research, and he says, "Hey, Warren, we're about to start an operations research program." And I knew at Princeton, at MIT, they had an OR program, one part of the campus, and then they had various departments like civil engineering. And so you had civil engineering over here, and you had OR over here. And the OR people didn't seem to know about a problem, and the civil engineers were very weak mathematically. Oh. And I said, you know what? What you need to do is, if you want to do transportation, do it inside of operations research, so that the intellectual training is operations research, which makes it fairly mathematical. But then you pick a problem. Now, I'm just describing the field of operations research. This describes 90% of operations research. There are some pure theoreticians. There are some people who are very, very, very applied, but the main core of operations research is people doing mathematical models and algorithms, usually in the context of at least one serious application. I mean, I think that's most of the field of OR. So I went in there, we set up this operations research program we already had this existing base of basic engineers. None of us like this term basic engineering. We thought that was a stupid term. And now there was a transportation program inside the civil engineering group, but every time a student said, "I'd like to do transportation," I would say, "Oh yeah, that's great, but you have to do it inside the OR program." Okay. So we moved transportation inside of OR, built up OR, and that has gone very well at the undergraduate level. And then I was off and running in the 1980s. So a hot topic was freight transportation, because it was just emerging from deregulation, and that was the first 20 years of my career.
Yeah, so during the 80s, you proposed several stochastic models for truckload trucking.
Truckload trucking. Yeah. I just have to tell, I'm sorry, I have to tell this one dinner conversation, 1982. My former office mate by the name of Woody Richardson, he just retired, was out at Schneider, and he had a boss by the name of Mike Crow, who had a master's in operations research. Schneider had already pioneered these deterministic models that would optimize over a week into the future, but you had to pretend you knew what was going to happen. Truckload trucking is an inherently noisy industry. Stuff is happening randomly over the time. Shippers are calling in. It's almost like Wall Street. And so Mike Crow was traveling back east, and Woody says, "You got to have dinner with this guy, Warren Powell." So we had dinner, and Mike Crow sat with me and says, "Warren, we've got these models that pretend you know the future." And he knew what the word stochastic meant. He says, "Warren, but the problem is stochastic. Now, could we possibly give the shippers a discount if they would tell us farther in advance? What type of a discount could we give them?" And I just sat there over dinner and went, "Oh my God, what a great question. Not only do I not know the answer, I don't know how to think about it." And I just sat there and I just decided that's what I'm going to do, because truckload trucking is quite rich, but I can explain the problem in under 10 seconds. You have drivers and loads, you match drivers to loads. You've got to figure out which load to move. You've got to figure out which driver to move it, where you have to think about the future. And I don't know what's going to happen in the future. So that blending of decisions, and it's not just moving one truck around, it's moving a whole fleet. So you have high dimensional decisions with uncertainty in the future. That mixture of decisions and uncertainty was just fabulous.
It's somewhat similar to Uber in a way.
It's like Uber for trucking. Interestingly, Uber has a division called Uber Freight, where they are trying to be their own Uber for freight. But it's very Uberish. There is, by the way, a competitive company called Convoy also doing the same thing. But it's drivers and loads, match drivers to loads. Where things are different with Uber is the driver is an outside contractor. Uber will pick a trip for you. You do the trip, but then Uber doesn't care about where you end up. In truckload trucking, you do. You have to think about eventually getting that driver home, or making sure he's getting good load. So you have to think about the future. So that became the problem I just always wanted to work on.
And you put a lot of effort, as I was saying, in devising several stochastic models. And you compiled those ideas in what you now refer to as your museum paper, right?
So there I was struggling with, how do you model this where you have decisions and information. So my only real background was this field called dynamic programming, Markov decision processes. And Markov decision processes is a fabulous tool if you're managing one truck. So you can say, I have one truck moving around the different states. So that truck maybe is in the state of Texas. Hey, I have different loads. What load should I move? And you can take the framework of Markov decision processes, and if you had one truck, you could do a pretty good job with it. But we had hundreds and hundreds of trucks, and it didn't scale. It blew up in this massive curse dimensionality. So I struggled around trying out other fields. There's a field called stochastic programming. I tried doing my own nonlinear models, whatnot. I ended up with 4 fundamentally different ways of modeling the problem. I wrote them all up. None of them worked. None of them came close. Either you couldn't solve them, or if you could solve them, you were solving such a simplified model that it was worthless. And I wrote it all up to say, look, I'm out of methods. I just don't know what to do. And so I went rolling into the 1990s, at which point this whole field was exploding. And I moved forward just thrashing around in the jungle, making up things as I go along, because, at the end of the day, you can always hack something together. And it wasn't until the late 1990s that the hacking started to come together as oh my gosh, this seems like a way to go about thinking about it. But that's at this point I'm 20 years into my career.
Yeah, during the 90s, you founded the Computational Stochastic Optimization and Learning Laboratory, better known as CASO Labs. And then you got involved in a series of transportation projects with many companies such as Yellow Freight, Canadian National Railroad, and even the Embraer from Brazil.
Sure.
Can you comment about it?
Sure. So the 1990s was, I almost, at times I sort of thought my career really should have started in 1990 instead of 1980, because the one thing that was really starting to happen in the 1990s was computers were starting to become way more widespread. In the 1980s, mainframes were just awful to work with. PCs were really a bit silly. So they had these Unix machines that were starting to become useful, but the 1990s was when computers really started to come to the forefront, where serious computing power that was affordable and accessible. So this was the early explosion of the information age, was the 1990s, and suddenly companies all over the place. You mentioned Canadian National. Our big railroad project really was with Norfolk Southern. And so I had a PhD student who started with me in the early 1980s. He was my first PhD to graduate, Hugo Simeo. He was
Brazilian guy.
He went back to Brazil to teach for 3 years. And after 3 years, he said, Warren, I think I'd like to come back. That was 1990. And he was basically the one who started CASO Lab, because at that point in time, all the projects was either me doing the coding or grad students doing whatever the grad students could do. But Yellow by that time had given me a very large project that I says, okay, I need to hire somebody to come in and do this coding. Hugo was emailing, by the way, very early use of the internet here. I mean, emailing hadn't been around very long, but we started emailing back and forth. But I do have one printed letter that I still have of this was pre-email, where I wrote out this whole letter. I found this in my files just a few months ago, where I could sense that Hugo was maybe ready to leave Brazil. And I had this big project with Yellow that was too big for me to do alone. I needed a full-time staff member. And by the way, it really couldn't be a grad student. So Hugo comes up, 1990. He is really what started CASO Lab. And we had this nightmarish a decade of projects raining in on us. I ended up hiring, by the end of the decade, I had 4 full-time programmers in addition to the grad students, whatnot.
Wow.
Norfolk Southern, Yellow Freight was a big one. Norfolk Southern was a really big one. And then I had a handful of other projects in truckload and whatnot. Truckload was tough because truckload carriers generally didn't have the funding for research. Secretly, truckload was the problem that I always wanted to work on. But whatever. The one theme in everything was they had decisions and uncertainty. That was the one thing that I kept in all the projects.
You then co-wrote yet another compilation article on dynamic resource transformation problems that you refer to as the Uber modeling paper.
Yes.
In which you introduced many concepts that you still use nowadays, by the way.
Yes. All my deterministic friends had a standard modeling framework, usually some form of multi-commodity flow. there was no standard modeling framework that involved decisions and uncertainty. But at the same time, separate from the uncertainty dimension, I was working on, first of all, I was working directly with companies. And I found that the academic models, especially multi-commodity flow problems, the modeling notation wasn't up to the real problems. It just didn't work. And I had friends dedicated, oh my gosh, the great problem to be solved is multi-commodity flow, especially integer multi-commodity flow. And I finally came to the realization that says, no, that's just not the real problem. Because I would be managing these resources. As you work with industry, a resource could be a driver or a locomotive. These resources were really quite complicated. And you couldn't just say there's 5 types of locomotives. A locomotive would have a whole vector of attributes. I mean, a truck driver, you didn't have a truck driver. You had a truck driver who lived in Texas, and he was at a certain type of fleet and hadn't been home for 10 days, and he was sitting in Massachusetts. And we ended up with like a 15-dimensional attribute vector. You can't model that with multi-commodity flow. And so I had to develop this whole notation for, and by the way, I invented the concept called resource layers. A driver is a layer, a tractor is a layer, a trailer is a layer, locomotive's a layer, train's a layer, you know. So you have different layers of resources. The biggest problem I worked on had 5 layers. I've worked on a 3-layer problem, a lot of 2-layer problems. But then you had this whole issue of modeling that flow of decisions and information. And it took me a while to get my arms around that.
Mm-hmm. You wrote a famous book on approximate dynamic programming, referred to as ADP, if you will. Did you expect to be that successful? And also tell me about the terminology convention regarding, you know, approximate dynamic programming versus reinforcement learning versus adaptive dynamic programming and so on.
So my feeling is sequential decisions, everybody faces sequential decisions. This is a universal problem that pops up all over the place. And there's a wide range of problems. It really shouldn't be surprising that I wasn't the only person working in that space. There were other people. And so what was happening is you have all these different communities all having their own pet problems. The finance people had their style problems, the OR people had theirs, and then the computer scientists got into the game starting in the 1980s, optimizing mouse and maze type of problems. And the computer scientists have their own history. They ended up calling what they were doing reinforcement learning. When I started doing this, you have to understand dynamic programming and approximate dynamic programming can be described as something that's almost obvious. I got into it by watching yellow freight dispatch drivers. And I realized that what I was doing wasn't working. But when I watched them do it, I went, oh my gosh, now I know how these people are solving these problems so much more easily. They make a decision now, and they only approximate the downstream impact of a decision now. So I came up with this downstream value. It took me a while. The same thing, parallel thing was going on in computer science with reinforcement learning. They didn't start off learning about Markov decision processes. They started off learning about a way of thinking and then realized, oh my gosh, this looks just like dynamic programming. But they were calling what they were doing reinforcement learning, and there's a history there that I could go into, but let's not. I was calling what I did adaptive dynamic programming. Somebody from National Science Foundation, Paul Werbos. Now, Paul Werbos, his dissertation, he comes from control theory. And his dissertation in 1974 was the first dissertation from the controls community to do what we currently call approximate dynamic programming. So he was spearheading this at NSF, and he saw me at an Informed workshop and said, Warren, you got to come to my new conference down in Mexico. So I went down there and I realized everybody was calling it either reinforcement learning, but I realized that was the computer scientist, or approximate dynamic programming. So I said, okay, I'll change from adaptive dynamic programming to approximate dynamic programming, because I realized that of the two names, I was sort of on the approximate dynamic programming side, because the computer scientists all had their own style and language and whatnot. So this whole thing of ADP and reinforcement learning, there were workshops called ADPRL, approximate dynamic programming and reinforcement learning. And so everybody understood that ADP and RL are the same thing with different accents. I call it American English and British English. Now, what's happened to all of us is we all get excited about this idea of making decisions, but when you make a decision now, it lands you in a future state. How do you approximate the value being in that future state? Cool. We all got excited about that. Oh my gosh, we can conquer the world. All of us thought that. We all were like, oh my God, this is great. And then we slowly all found that it didn't work as well as we thought. Okay. There were certain problems where it worked. And then as soon as you start exploring other problems, it stopped working. And so the RL community has evolved into their own mixture of methods, one of which has to do with approximating a value function. I ended up doing the same path.
Mm-hmm.
At one point in my lab, because I work on a wide range of problems, I realized, well, value functions work here, but they don't work here. And all of a sudden I realized that in my lab that the natural way to solve problems, a lot of these sequential problems, you look at it and you sort of have a feel for the right way to solve it. Okay, mm-hmm. there is a feel. Oh, that looks like a good way. In finance, you buy low, sell high. There's no dynamic program. There's no value function. It's just a rule. Mm-hmm. There's a lot of problems that can be solved with rules. But like if you want to get to a destination and you make a decision, you're going to solve a shortest path problem to the destination, and that will tell you whether to turn right or left. That's a look ahead policy. Neither of those use value functions. And so my earliest book, which I finished writing in 2005, it was published in 2007, mm-hmm. everything had to do with approximating value functions. Reinforcement learning, the first RL book appeared in 1998, mm-hmm. was all about approximating value functions. Mm-hmm. Look at the second edition of the RL book, it came out in 2018. It's a whole range of different methods. My second edition of ADP started strongly hinting at different methods. It's my latest book that has really blown that open. But we all, as we thrash around on different problems, we discover that that not every problem is a nail. Mm-hmm. And our hammer that used to be great for the nail, not everything's a nail.
Right.
And this is a process that everybody goes through.
Yeah, I understand perfectly. And in the meantime, you started to work in a topic called optimal learning. You even wrote a book about it, and you also expanded your range of applications beyond transportation problems at that time.
Sure. So a couple things are happening. First of all, starting around 2002, there was a big economic meltdown, and I started to feel that, when the economy was a meltdown, trucking and freight transportation suddenly didn't have any money. Yeah. I just started to think, after 20 years, I need to work on some other problem. Uh-huh. Energy was starting to become quite interesting. Mm-hmm. And so I wanted to flounder around. Now, if you work in approximate dynamic programming, one of the first things you will run into is what's called the exploration versus exploitation problem. Let me take my one truck problem where I have different loads. I have amount of money I'm going to make on the load, but then there's the value at the destination. Well, what if there's a destination I've never been to? I don't know the value of that destination, and so I might underestimate it, but maybe I should go to it just to learn. That's the exploration versus exploitation problem. Mm-hmm. So in 2005, I had a new student. I said, Peter Fraser, I said, Peter, we've got to work on this exploration exploitation problem. And we started with the problem as it exists in approximate dynamic programming, but then we kept making it simpler. Peter's a very good mathematician, and he wanted to get to the point of a problem where he could prove theorems. But we ended up with a much simpler problem that actually had nothing to do with the original dynamic programming application. And suddenly really cool stuff started to happen, and I just veered in the direction of, I don't care about managing a truck, let's just collect information. And it was beautiful because it was a lot simpler than the dynamic programming problems. The dynamic programming problems I was working on were all fairly complicated. Whereas collecting information, these are inherently simpler problems that we all encounter. Mm-hmm. And I just went rolling into it. It's sort of, just as I was moving into other applications like energy, suddenly I had this big shift away from ADP into this thing called optimal learning. I would later learn optimal learning is just a different type of sequential decision problem. Mm-hmm. Okay, that took a few more years. So I had a flurry of time, and I landed this mega project on how to do experimentation in material science. I got taken completely out of my comfort zone.
Wow, material science.
We were working with material scientists. Again, long story there that let's not go into, but I landed into this project of helping scientists decide what experiment to do next. That's an information collection problem. And all of a sudden I had a whole flurry of students working on optimal information collection. We had all kinds of various, it completely restarted my career.
Yeah, what a turn of events, actually, you know?
Yeah, and it was really funny because it really was because of my program advisor at Air Force, who's a former transportation guy, who knew me from his transportation years, but he lands at Air Force and he saw that I had co-authored a paper where we applied optimal learning in the context of a drug discovery problem. And he just made the connection that says, oh, that looks like chemistry. Oh, here's this thing in material science. Hey, Warren, you ought to take a look at this opportunity. And I went running across the street at Princeton to the material scientists and had a chat with them to find out, look, is there anything here? And they all got excited. And I said, okay, I wrote up a white paper. And suddenly for 5 years, I was working in material science, which is, let me just put it this way, great stories, great pictures. I mean, and this was all happening alongside the energy stuff, and those two were actually highly complementary.
Your work on energy motivated you to formalize the idea of parametric cost function approximation that you claim to be the most important contribution to the field of stochastic programming since the seminal paper on the topic by Dancing in the mid-1950s. Can you explain why? That's a very strong claim.
Okay, so early 2000s, 2007, 8, 9, this is when the whole climate change things really started to hit the public awareness, okay? And suddenly everybody went roaring into us. Now, the grid operators had these big optimization models where they sit today and plan for tomorrow. Well, let's say tomorrow you have a lot of energy coming from wind and solar. So wind and solar is highly stochastic. So all of a sudden there's this huge interest. So I landed a whole lot of money and started to build my own model of a grid operator. But my focus initially was, I just want to build a big simulator. I'll get to the optimization later. I really just wanted to focus on simulating. But a whole pile of people around the country, especially in the national labs. The national labs all have supercomputers, and they're always on the hunt for really, really big problems that need a supercomputer, okay? I mean, if you say national lab in the United States, what you really mean is somebody looking for a use for a supercomputer, okay? The national labs are a major source of funding to help the United States move forward with supercomputers. Anyway, so there were several groups, including different academic groups, all taking this technique called stochastic programming, where instead of, so in the classical methods, you plan today for tomorrow, you forecast tomorrow deterministically. This is what Google Maps does. It plans your trip into the future deterministically. And they were saying, oh, but it's stochastic. You can't do that. You have to optimize over 20 or 30 or 50 scenarios. So what was already a big integer program suddenly just became 50 times bigger. Oh my gosh, they loved it, and they got all excited and using supercomputers. And every year there would be a workshop down at the Federal Energy Regulatory Commission where everybody would come together and describe their latest work. Well, in the process, I was still off on the side saying, I just want to build this big simulator. I landed a joint project with University of Delaware that wanted to test offshore investments in offshore wind. So I had teamed up with them, and they were all excited. Everybody wanted to conquer the world with renewables and that type of thing. And I just was really much more focused on, in the beginning, let me just simulate. Now, at one point, I realized that we were running into, so we would simulate higher and higher levels of renewables, and occasionally, and there was one time in particular where we just couldn't get our system to work. We kept having outages that we couldn't make go away. And I said, you know what, Hugo, why don't you tell the model that this event is going to happen tomorrow? Give the perfect forecast. And what happened was that fixed the problem, but it fixed it in an incredibly narrow way. There was a spike where the wind really dropped at a certain time right around noon. And when you told the model yesterday that this was going to happen, it fixed it by scheduling extra energy for about a 20-minute interval. And I'm like, well, that's not anything. That's only going to happen if it actually happens at that point in time. That big downward spike, this is the problem where the wind is at one level and it suddenly drops. And this happens very easily. And suddenly you're caught short. And I went, oh my gosh, this idea of having 20 scenarios in the future, it's just never going to work, because not only is it going to happen, there's where is it going to happen? It's going to happen in this region. In the company I was simulating, they had about 7 major regions. And I'm like, really what you need is to have extra power at all points in time, because this big downward drop would happen at any point in time.
Right.
So guess what? That's what they were already doing. They would have these tunable parameters in there that said, oh, we just want to make sure we have extra generation capacity. And I'm like, oh my gosh, what industry was doing was the right way to solve the problem.
So you learn from them, actually.
Oh, yeah, absolutely. By the way, my ADP stuff I learned by watching Yellow Freight solve their problem. A lot of my tricks came from watching how people did things in the real world. And so I had this, I said, oh my God, the problem they have is they're solving it the right way. They just don't have fancy words and fancy math.
Yeah.
So I came in and I said, okay, I'm going to set this up mathematically in the proper way. We're going to call it a parametric cost function approximation. So you have a deterministic function, but you have tunable parameters. It's like a parametric model, just like any parametric model. Like you're trying to, estimate demand as a function of price, and you think it's some downward sloping curve. But now you're parameterizing an optimization model. Incredibly powerful idea.
Mm-hmm.
They just didn't have the fancy words and the fancy math. And a lot of people put these tunable parameters into their models. The thing is, they don't tune them. The grid operators do. Every single day, they sit Monday and plan for Tuesday. Then they get to Tuesday and they say, let's see how well we did. Did we need to do any tweaking and tuning? So they didn't do it mathematically, but they did it.
Right.
And I said, oh my God, now you have to understand, stochastic programming with scenario trees fills the academic literature, thousands of papers every year.
Mm-hmm.
None of it ever you put into practice.
Right.
I mean, it's just the ratio of papers divided by real world applications has to be higher than anything that I know about.
Mm-hmm.
And so, whereas the idea of doing deterministic models with tunable parameters, that's standard industry practice. They just don't do it in a formal way, and they do a pretty ad hoc job of the tuning.
Mm-hmm.
So I presented this idea at one of the FERC workshops, and one of the big grid operators, our big, what's called the Midwestern, it's called Michel, was sitting in the front row, staring at me and going, oh my God, this is great. Do you have an algorithm that we could use? And I had to say, to be quite honest, what you're doing in the field is better than anything that we could do with an algorithm. But they just loved it because it formalizes what they're already doing.
Absolutely, yeah.
And so if you want to do something where you're guaranteed to be useful, do this. Now, it's not a panacea. It's not going to work for every problem.
Mm-hmm.
But stochastic programming has been around for 60 years and nobody uses it. Mm-hmm. So it's the technique that's already been researched to death that nobody uses. There's a fundamental change of thinking because in stochastic programming, they think the problem is how to optimize into the future. Whereas I think the stochastic optimization is the real world or a simulator where you do an approximation in the future with tunable parameters and then you tune it in your simulator or sometimes in the real world.
Right.
And the grid operators, they don't have a simulator. They use the real world.
Right.
In my lab, we use a simulator. We do carefully designed simulators. So it changes where the stochastic modeling it is.
Yeah, I see what you mean.
Stochastic programming, it's a stochastic model of the future, whereas in my method, the stochastic model is in the simulator.
Right. Because of your talks available on YouTube, I now always think of a jungle when I come across a stochastic optimization problem. and I once heard you saying that the reviewer made a comment, hey, come on, it's not a jungle, it's more like a garden.
Yes, that cracked me up. So when we academics write papers, we write it up and send it to a journal and it goes out for referees. Referees can be a little abusive. One thing about sequential decisions under uncertainty, it's not one field, it's about 15 different fields. And you're never guaranteed to get referees in exactly what you're doing. And then if you try to write a paper which is doing something brand new, one of my early ADP papers was rejected because I had already written an ADP paper and the area editor says, oh, you already wrote an ADP paper, so this is just yet another ADP paper, it's too incremental.
Oh.
I'm not kidding, okay?
Oh.
The parametric CFA paper, we're still struggling to get accepted. And the referees, I have put a rebuttal, not in a letter, I have made a web page. In time, I'm going to launch it, but fortunately at this journal, the Journal of Computing, I was able to find an area editor who actually invited me to write a paper where it'll be a feature article. They call it a feature article, and they actually will have people writing public rebuttals in the journal. So there's sort of a little back and forth debate. And I said, oh my God, that would be great, because what I really want to do is have at least one person from the stochastic programming community, so that we can get a little back and forth discussion going on. But I've had a number of papers that get rejected just because the referees just don't know what they're talking about. And you know, this is a field where when you make decisions under uncertainty, in deterministic world, there's a standard modeling framework and sort of a standard approach to go after designing algorithms, and people have an idea when you've done something new. When you have sequential decisions under uncertainty, it's a big mishmash. Okay. And, you know, somebody from stochastic programming could end up looking at a paper on approximate dynamic programming. People don't even know what ADP is. Reinforcement learning, which is just exploding in popularity, nobody knows what it is. So I have a web page, tinyurl.com/what-is-RL, and that's my attempt at defining reinforcement learning. In the 1990s and early 2000s, reinforcement learning was an algorithm. It was approximating value functions. It's a form of ADP. But over the years, people discovered that doesn't always work. In fact, I claim it usually doesn't work. The field has exploded into other techniques. So today, a very prominent RL researcher, Ben Van Roy at Stanford, was at a conference, and he defined RL really more as a problem than as a method. So that's all described on the webpage. So if you go to the webpage, I have the whole description of what Ben does in my version. My feeling is we shouldn't really get into debates of what is RL or that kind of thing. That's kind of silly. Let's just talk about the problem class is sequential decisions. Even Ben realized, yes, every reinforcement learning problem is a sequential decision problem. Decision, information, decision, information. Okay. Every stochastic optimization problem is decision, information, decision, information, decision, information. So the problem is sequential decisions. That's the problem class. So what's the method? Well, there's this jungle of methods, but I found that they can be drawn into 4 basic classes, which divide into 2 major subgroups. The look-ahead subgroup, which is what the academics really like to do, and the group of, let's just find a good function that works well over time, like buy low, sell high, or order up to. Let's just find a good function. It's not looking into the future, but it's just a good rule that seems to work well. Now, all 4 of these methods, any one of these 4 methods can be perfect for some problem. I'm quite positive that we're not going to come up with some method that dominates all 4. I don't think we will ever have less than the 4. So far, nobody's come up with a 5th. And when you really get to learn them, you realize, yeah, the way he's defined it, there's really only the 4. The nice thing about the 4 is, now some of the 4, so the 4th is direct look-aheads, and that's not just one field, that's multiple fields. But I think it's valuable for people to realize, yes, you're working with a CFA class, but maybe you should look at a VFA class or a DLA class. It just makes everything more visible. And so all of a sudden, I've realized that if you have a sequential decision problem, I guarantee you, no matter what you do, you will end up using one of the 4 classes. Even if you never read my book, you will end up using one of the 4 classes, maybe a hybrid. And at that point, I started to realize, you know what? I'm not so tied up about how to solve the problem. I know how to solve it. I'll use one of the 4 classes. I've got the roadmap. I end up now focusing more on modeling the problem and what is the problem and what is a decision, and that wonderful question of what are the sources of uncertainty, which is, by the way, much more interesting. I had somebody at an Army workshop, Army research office, in the middle of one of my presentations just look at me and says, I don't care about optimal policies. What he cared about was modeling uncertainty. And in many real problems, it's understanding uncertainty that's more important than coming up with the world's best decision. Now, he overstated a little bit. I mean, I like to have as the guiding principle optimal policies. We never reach it, but you like to have it as a guide. But what do you mean by optimal if you've modeled the problem incorrectly? The thing is, in more complex problems, let's take a supply chain problem. You're going to start off with a basic problem and then make decisions. But as you make good decisions, you're going to realize that your model of the problem needs to be better. Now your decisions need to be better. And you keep climbing this ladder because there's a rich array of sources of uncertainty, and you're never going to consider all of them. And there's not just one decision. You're not just ordering inventory. There's a whole family of decisions to be made. So you sort of almost have to climb this ladder. And I like to say, start off with a basic model of uncertainty, go work on decisions, get a good model of decisions. Now go work on your uncertainties and keep climbing.
Yeah. You spent the last decade trying to design an universal framework for sequential decision problems. And you were just mentioning about the 4 classes of policies that you firmly believe it's very generic. And you even wrote several papers as an attempt to find a definitive approach. Do you think you have finally found the Holy Grail?
Yeah, absolutely. Absolutely. I've nailed it, and it's in my new book. It was a series of papers. The real modeling of the problem, I actually pretty much figured around in my first ADP book. I had a chapter dedicated to it, chapter 5. And if you go to castle.princeton.edu/ADP, you'll see that I've had chapter 5 on the internet that anybody can download for free, and it's only a modeling chapter. All it says is how to model. So I figured out the 5 parts of model, which is state variables, decision variables, exogenous information, which is the random stuff, transition function, which is the equations that describe how state variables evolve, and finally the objective function. So a deterministic guy like you, when you sit down to a deterministic optimization problem, everybody knows the fundamental point. You've got a vector x, you've got an objective function, you have constraints. Boom. And that's a wonderful framework, and there's a lot of richness, and there's still a lot of hard problems we don't know how to solve in that class. But everybody starts by writing it the same way. Yeah. That's not true in sequential decisions. So in chapter 2 of my book, section 2.1, I list 15 different fields. And at the end, I stop and say, well, wait a minute. One of the fields must have gotten it, I mean, they can't all be wrong. And I say, yeah, optimal control. They're the ones who come closest. I've had optimal control people look at my modeling framework and they say, yeah, that's just what we do. And I would say, yeah, but there's some key tweaks. And one of the major tweaks, because the word transition function, only optimal control uses that. That's where I got the idea of a transition function. Now, they make the mistake of blending the model with how to solve it. And they fall in the same trap the Markov decision process people do, is they blend together the model with how to solve it. And DP people think Bellman's equation. You always go to Bellman's equation. And that's the big mistake, because Bellman's equation can be useful. It might be useful. But let's just imagine there's a universe of people out there making decisions, sequential decisions with uncertainty. How many of them have even heard of Bellman's equation? Almost none. Okay. Bellman's equation cannot be the answer to everything. In fact, I think it's actually rarely the answer. Of my 4 classes of policies, the policy function approximations, PFAs, the cost function approximations, value function approximations, and direct look-aheads, you go out in the real world, you're going to see PFAs, you're going to see CFAs, and you're going to see deterministic look-aheads like Google Maps. Almost never do you see value functions. So I love value function approximations. I have found some great uses for it. But in the universe of decisions, almost never. Okay, there's some handful of problems where Bellman's equation is really useful. I have found some. But the vast majority of real world problems, you need all 4 classes. Now, the PFAs and the CFAs are the simplest. The VFAs and the stochastic deterministic look-aheads, direct look-aheads, are more complicated. There's a line that I like. It says, well, why doesn't everybody just do what's simplest? And the line I like to say is, with the PFAs and CFAs, these are the simplest, but the price of simplicity is tunable parameters. And tuning is hard. Right. So anybody says, oh, no, your method is way too complicated, I've got a much simpler method, I guarantee you somewhere in its simpler method is tunable parameters. But
that you learn from the industry, correct?
Yeah. Yeah, industry tends to know, buffer stock, schedule slack, there's all kinds of tunable parameters. The problem with industry is they don't tune. Sometimes they do. Like the grid operators, they had these reserves for energy, for uncertainty, and they tune. They tune it. Not mathematically, but they tune it. But an awful lot of models in industry, they put in the tunable parameter and then they just go on and they never tune.
Right.
Buy low, sell high, order up to. Those are 2 tunable parameters. I'm guessing they rarely tune them.
Right. So Warren, I know there is an interesting motivation behind the title of your book. And what is the audience to expect to attract with it?
So this is really a fundamentally new book. It really should be called Sequential Decision Analytics and Modeling. So I have a set of lecture notes that I wrote with that title for an undergraduate course, and I'm turning it into a book. It's sort of a companion book. My new book references the sequential decision analytics and some of the exercises are built from it. I would love to have titled the book Sequential Decision Analytics, but nobody's heard of it. And I'm sorry, at the end of the day, books are only useful if people buy them. And Google searches matter, and nobody's heard of sequential decision analytics. Google the phrase and nothing comes up. So I Googled a whole pile of phrases, and there were four, let me see, the top three. Number one, really standing out, reinforcement learning. This reinforcement learning is just taking off. Everybody wants to do reinforcement learning. The optimal control is one, but the optimal control people are starting to adopt reinforcement learning. There's another phrase called stochastic optimization, and that is also, to my surprise, is not only popular, but it's growing in popularity dramatically. If you look at the number of citations of a lot of these phrases, and if you go to my What is RL webpage, you'll see the graph of all of these. From 2015 to 2020, reinforcement learning and stochastic optimization are growing dramatically in popularity, which surprised me a little bit. Reinforcement learning, I had one of my students say, well, you absolutely have to have reinforcement learning in the title, and it has to come first. And you know how he described reinforcement learning? He says, reinforcement learning is stochastic optimization without the math. I loved it. This was one of my civil engineering students. I make the title reinforcement learning and stochastic optimization because these are the most prominent phrases. Old reinforcement learning is way too narrow, but reinforcement learning today is a massively broad field. Nobody knows what it is, but every reinforcement learning problem is a sequential decision problem. And if you work on sequential decisions today, certainly in academia, they're going to call it reinforcement learning, whatever. I just do it for sales. You won't see me using the term reinforcement learning very much inside the book.
Right.
Because what I'm trying to do inside the book is provide good balance across all the fields, including optimal control, which, by the way, I think optimal control got a real short shift. They invented most of these concepts. They did everything first. They have the best modeling framework. And they're just getting left by the wayside, and everybody's running after reinforcement learning. The computer scientists are just better at, and by the way, they have great successes like SpaceX. I mean, I guarantee you, SpaceX with its dramatic ability to land and turn around, and that's all optimal control.
Yeah.
But the computer scientists solved the Chinese game of Go, and that's what got the newspapers. And so suddenly everybody's doing Go, and Congress knows about reinforcement learning. So we all roll with it. Yeah.
So at the end of the day, you are targeting a large audience.
Yes.
And how do you address the issue of notation in your book?
I have a whole section in chapter 1 saying, okay, here's how I get through notation. So you have to have a state variable. So what do you use? So unfortunately, this is where I really have problems with optimal control, because everybody calls the state variable S. That is the standard notation for state, except in optimal control where they use X. The problem is, what's a decision? So the reinforcement learning people adopted the notation of Markov decision processes where they have A for action. But A almost always, 99.9% of the time, is a discrete action. Now, the problem is you have this extremely large, successful, and mature community called math programming, and they use X. And X can be binary, it can be discrete, it can be continuous, it can be a vector, it can be anything. I'm sorry, if you're going to do optimization making decisions, you have to draw in the field of math programming. And even the computer scientists, there's a sub-community doing what's called multi-arm bandit problem, they adopted X. So I said, okay, S for state, X for action. Now, the exogenous information, there's almost no standard notation for that except in optimal control. And they call it W. Now, they use lowercase w, and little wt is random at time t, which does not make sense. It's just the wrong notation. And my probability friends at Princeton like to have capital letters as random. So I said, let's do capital W, but capital WT is known at time t. So if you're in a state at time t, st, you make an action xt, and then you observe new information, that'll be wt plus 1, not wt, the way many controls people do it.
Mm-hmm.
So that really nails it. There's one last issue which has to do with this crazy thing called, what in the world is a state variable? Now, there is only one community out there where you can open up a book and see definition, state variable. A state variable is only one community, optimal control. That's the only community. All the other communities will just use the word state in a sentence, or there's some major books by, for example, Bellman.
Mm-hmm.
And then 40 years later, Putterman's wonderful book, award-winning on markup decision processes, where they will use a definition that says something like the state is the state of the system.
Mm-hmm.
They literally use the word in the definition.
Mm-hmm. Yeah.
And then I can point to places where I'm like, they clearly don't know what a state is. Because a lot of people think state is a physical state. Like if you're running around a graph, it's what node you're at. Or if you have inventory, it's how much inventory. State is information. It's really the state of knowledge. It can be a belief.
Mm-hmm.
And you've got to get used to that notion. And I can show you examples of award-winning books where they clearly do not know what a state variable is. Okay. State variable is the state of knowledge. So it can be physical resources, it can be information like a price or weather, but it can also be a belief about something that you don't know perfectly.
Mm-hmm.
And that nails state variables. Okay?
Right.
Now, a lot of people, anybody doing something to do with dynamic programming, you get a sequential decision, and you say dynamic programming, and they're going to say, oh, and now I have to solve it with Bellman's equation. And that's the other thing that I'm just like, no, no, no. 4 classes of policies. You're going to need to look at all 4. I have no idea which one will be the best one for your problem.
Right.
And only one of them uses Bellman's equation.
I see. So what is the relationship between machine learning and sequential decisions?
So I actually, when I talk about optimization, you know, it's fun to compare sequential decisions as an optimization problem to deterministic math programming. I actually like comparing sequential decisions to machine learning. So in deterministic optimization, you're trying to find X. You're trying to find a vector X. It's a vector of numbers. Machine learning, you're trying to find a set of functions. They call them statistical models. Neural network, a linear model, a parametric model, whatever it is. You're searching for the best models, and then once you've picked a class of models, you're searching for within the class. Okay? Mm-hmm. Now, models come in 3 broad flavors. Lookup table, parametric, non-parametric. Anything that you do in machine learning, you're going to have a lookup table model, parametric or non-parametric, and maybe a hybrid. Okay? And I draw these as overlapping circles. When you do sequential decisions, you're also looking for functions. It's just we call the function a policy. And just like machine learning, you have to search over functions, and then you have to search within a class. The difference is that in sequential decisions, there's 4 classes, one of which is every single class of function in machine learning.
Okay.
The first PFA class, there's a one-to-one relationship. Anything that you might do in machine learning is a potential policy in sequential decisions. All the other 3 classes of policies are all themselves optimization problems. If you have a policy that is not itself an optimization problem, you're in that first class of a PFA.
Okay.
And fitting the best PFA and fitting the best statistical model, the only thing different is the statistical model needs a training data set. In sequential decisions, you don't need a training data set. You need a model.
Model, yeah.
Okay. You need when you're doing a math program, you have a model, you have the constraints, but you don't have a training data set. Okay. So in sequential decisions, we don't need a training data set. We just need a model of the problem. But when we go to look for policies, the PFA class is a one-to-one relationship with everything in machine learning. But then you had these other 3 classes, the CFAs, VFAs, and DLAs. All of them are themselves optimization problems. Now, the computer scientists, the CFA class, they have a very powerful policy for multi-arm bandit problems called upper confidence bounding, where you say, hey, I have a set of discrete choices. Here's my best estimate of how good a choice is, and I have a level of uncertainty. And my policy is to take how good it is plus a parameter times the standard deviation and maximize that, do an argmax. So that's an optimization problem, a very simple optimization problem. Once you realize there's an optimization problem, there's nothing to stop you from bringing in powerful packages like Cplex and Gurobi and suddenly making your set of decisions to be, well, the sort of things that we do in deterministic optimization. So you suddenly open up the door to these dramatically richer problems that the reinforcement learning community is utterly unaware of.
Yeah, I think the communities have to communicate better, so they can, find a good hammer and, at least be aware of what's going on and in the new field that you're calling sequential decision analytics, right? It encompasses so many things, and it's a very elegant way of generalizing a lot of ideas.
The hardest thing is the jungle is a true jungle. Everybody in their little piece of the jungle, they speak a certain language. They have a certain group of people who are considered the leaders. So each one has their little pyramid, and each has their group of people who are stars. I was giving a talk on this out at Berkeley, and a good friend of mine, Shmuel Oren, over dinner, he says, Warren, the academic community isn't going to like this. And he was right. He was absolutely right. Because throughout the jungle, you have these stars. Okay, here are the stars here, and here are the stars here. And here I come in, and I'm not minimizing what anybody's done. You still need all of this great work. I like to say that I'm standing on the shoulders of giants, and I think I've made some contributions, but a lot of what I'm doing is just pulling together the work of everybody else. And I like to think that there's whole people who've never heard of stochastic programming. I mean, there's a lot of people who've never heard of these fields over here. I'd like to think that I'm giving them greater visibility. Now, the parametric CFA class, with the exception of, well, it's an industry heuristic, and this, the computer scientists have invented something called upper confidence bounding, which is a CFA policy. Nobody knows about it, and I think that it can be a little bit threatening, because people get so accustomed to the idea that if you want to do stochastic, you have to look into the future and model the uncertainty in the future, and that's just not true.
Right.
Okay, like order up to policies do not look into the future. They don't model the future. They just have an order up to, and they can prove theorems. I mean, that under the right conditions, that's an optimal policy. But there are other problems where you just have to look into the future, like Google Maps. Now, Google Maps is a great place of where deterministic approximation for finding the best path is really quite good.
Yeah.
Here's what it's not good at. Let's say you need to make an appointment by 9 a.m. and Google Maps says it's going to take you 40 minutes to get there. Are you going to leave 40 minutes before your appointment? There's two decisions going on. It's not just what's the right path, but what time do you leave? I'm going to take the 40 minutes from Google Maps, and I'm going to add in a 15-minute buffer. Now, let's say I do this over and over again, and I find that every so often the 15-minute buffer isn't quite enough because of uncertainty. I'll bump it up to 20 minutes. That is a parametric cost function approximation, and we all do it.
Yeah.
We just don't do it with the fancy math.
Yeah. So you're taking something that is quite intuitive and formalizing and, transforming that into math so we can embed into a model that effectively solves the actual problem, right?
Yes.
Yeah. So Warren, let's change.
I'm very excited about that.
Yeah. It seems very exciting in the end. So let's switch topics a little bit. Why did you decide to retire from Princeton?
Well, so it was complicated. My department has never been an easy department. I came to Princeton to start operations research. I concluded that it failed. I'm the last OR person in my department. There's a couple very senior people who affiliate with OR, but they pretty much dropped out, and they don't have a single person under the age of 60 who identifies with, say, the informs community. So operations research was sort of dying out. My book still had quite a bit of work to do. Oddly, my whole lab and whatnot was extremely popular. And I had this picture from March of 2019, where I had 27 grads, undergrads, postdocs, staff. I had a huge group.
Wow.
And I had people piling on me. And the thing is, my style of doing work was very popular. Princeton has a tendency, and it's not just Princeton, but to hire theoreticians. You know, the students, they're okay with theory. They're really good at math, but they want to do computation. They want to solve problems. And my work was very take a problem, do a fancy algorithm, and then go prove your theorems about it. Okay. And when you take sequential decisions, I'm telling you, deterministic optimization is sort of a maturing field. There's still a lot of hard problems, but it's a maturing field. Linear programming is kind of dead. Convex, a lot of convex nonlinear stuff is very mature. There's sort of some pocket problems. You get into the world of sequential decision problems, and there's still fantastic problems. We've got some basic problems we've been working on since 1950s. We still don't have good algorithms, a classical stochastic search problem. Once you start putting in uncertainty, it gets really rich. You will never run out of things to do, and you never run out of finding an application, because you just have to take what's the hot problem today. Oh, climate change, sure. COVID, sure. Whatever. Go. I had a student start with me, and this was just pre-COVID, but wildfires were really hot. So he did a whole thing on drones with wildfires, and then halfway through that paper, COVID hit, and he says, "Okay, I'm going to put the wildfire paper off to the side, do a COVID paper." He did this great COVID paper, came back, finished the wildfire paper. All you have to do is open up the newspapers to find a good sequential decision problem.
Yeah. So you have a company called Optimal Dynamics with your son, and you're putting these ideas into practice.
Yeah, well, this was another thing, because my son graduated 2014 and he was looking for things to do. And I said, you know, I've got this big model that we did for Schneider National, and it's just sitting on a shelf. And so he grabbed at that opportunity, and it's just been fabulous. So the idea that I could spin off from Princeton, finish my book, but help my son with his company. And my son, we now have an analytics group with about 4 or 5 people. The company's up to about 45 people.
Wow.
My son, by the way, has amazing business skills. He didn't learn them from me, but he's fabulous at the business side. So we just finished our Series A funding, so we're very well funded. And he's hired, you know, a great group of people. We've got the engineering, we have the software, we have the people management, we have the sales, all the different dimensions. CS in academia is called computer science. Well, in industry, it's called customer success. And so we're actually now seeing these tools go into industry, and it's interesting. It's you know, the tools are great, but it's hard. There's a lot of work that still has to be done. But it's a little bit like I built the engine, a good engine, not perfect, but we have to build a car, and then we have to build the car company. And so my son isn't just building the car, he's building the car company, so that we can take this, at least initially, throughout the trucking industry, and then hopefully on problems beyond trucking into supply chain management. So that's extremely exciting. If you go to the tinyurl.com/OD white paper, one word, so optimal dynamics, but just the letters OD white paper, you can just skim the paper. And if all you do is read the section headings, you'll see that we're using all 4 classes of policies. This is a white paper with a bit of math in it. And it shows that we're taking exactly this theory. And every time we come up with a decision problem, so there's a lot of work out there in machine learning and whatnot. Machine learning has become a little bit of a commodity product. There's thousands of people graduating from schools. You take a data set, there's standard software. It's a really established field. There's PhDs there, but most of the people have master's level education. Decision analytics, this is the next wave. This is a wave above it. Computer scientists like to call reinforcement learning just a part of machine learning. I really believe they're wrong. I think decision analytics is a whole step above machine learning. There's much richer. There's the whole 4 classes of policies. There's the modeling. There's dealing with uncertainty. I think it's much richer, and I think it's the next wave of getting computers to actually make decisions. So machine learning doesn't make decisions. Reinforcement learning does. Imagine playing the game of Go. You're making decisions. But now let's take that and move it to a trucking company or a supply chain. Oh, things get a lot richer.
We can spend about the next hour or two just talking about, or even days, because there's just a lot of applications. What
I have found in what I'm doing is Now that I know that at the end of the day, you're going to look at the 4 classes of policies and pick among them, I find myself less focused on how do we make the decision and more focused on, am I modeling the problem correctly? So first of all, it's some of these more complex problems, like what is the decision? It isn't always that obvious. I often know the goals. You know, I want lower costs, I want better response. My daughter works with epidemiologists and opioid crisis. I'm like, you know, what's your decision? And her typical answer was, well, I want to have fewer deaths. And I'm like, that's not a decision, that's a metric. So, you know, you come up with your metrics, but then what are the decisions? These complex problems, coming up with the decisions is actually quite hard, but not nearly as hard as identifying all the sources of uncertainty. Mm-hmm. So how can you solve a problem if you haven't articulated the decisions and the forms of uncertainty? So this is something where you don't need to be a mathematician. You don't necessarily need to know any math, but you do need to know what's the right question. And if there's one thing that I think the exercise of putting things on the computer is fabulous at doing, it's telling you the right question. When we humans try to solve problems, we're very complicated and messy, and we have our way of muddling about. Computers are not. Computers are really specific about that you have to articulate the problem in a precise way, and then here's the decision, and here's the information you need to make the decision. And it forces utter clarity, mm-hmm. even into complex problems.
Yeah. I know you have good connections with Michel Gendreau and Crainic from Montreal. To conclude our conversation, do you have any interesting stories involving them?
Oh, well, MIT is a great university, very admirable, but the transportation program, when I was graduating, was in early stages of completely collapsing. And just as I was graduating, I could look behind me and realize that it was just failing. But there was this fabulous group up at the University of Montreal. Back there, then it was called the Centre de Recherche sur les Transports, or CRT. And this was known around the world. And leaders like Mike Florian and Jean-Marc Rousseau had gotten this started. And they just had this fabulous little niche where they had access to these French-speaking students that had nothing else to do if they weren't going to come there. So fabulous group, and they just built this transportation group that became renowned, and they were so welcoming. And so they got to know me very quickly. Michel Gendreau and I are sort of separated at birth. Our birthdays are about 2 days apart. Without knowing each other, we both had dissertations on identical topics of bulk service queues, mm-hmm. which neither of us pursued later in life, but we both started on the exact same topic. We have roughly the exact same age. Both of us roughly working on our own, because his advisor knew nothing about bulk service queues, and I didn't have anybody at MIT who knew anything about bulk service queues. So we got started, but it was Crainic was the first one actually working in trucking problems. And so I would go up to Montreal, and there I was working on my trucking problems, and Michel's advisor, Mike Florian, said, oh, well, there's this guy, Crainic, you should get to know him. So Theo is fabulous and you know, just a joie de vivre that's infectious. And so he and I at least were two people who could talk to each other, because there weren't very many people working in the trucking industry. Uh-huh. And so he had his particular style. Working in Canada versus the US is very different environments. But I remember at one point in the 1980s, I started to realize that there were no conferences for operations research. And I went to Theo. And the nice thing is, so at Princeton, I didn't have any infrastructure, but they had this fabulous center, the CRT, which is now called CIRRELT, mm-hmm. CIRRELT, and I won't try to do that in French. But they had this wonderful infrastructure that was well-funded. And so we said, you know, okay, we need a conference for transportation, but for the OR community. And it ended up being called Tristan. There was a little play. There was another conference in operations research on facility location called ISOLDE, mm-hmm. ISOLDE. So somehow it came out that there was Tristan. Mm-hmm. Tristan is still taking place once every 3 years. I think our first one was early 1990s. I think early 1990s. And it's been cranking along every 3 years, always in some weird location. I finally dropped out because I couldn't handle the travel. Mm-hmm. But it's been wonderful. And having the group up at Montreal, this has been a group where I keep going back there, and a lot of the research I've done is not heavy math and algorithms. It's just modeling and words and vocabulary. And Theo arranged for me to get an honorary doctorate up there. And that was the time when I just was coming to grips with my 4 classes of policies and my universal framework. And I gave the universal framework and I said, you know, this is like cloud to cloud lightning. It's very pretty, but what can you do with it? I wonder what it was like being in a classroom with Kantorovich in the 1930s when he put up the first linear program and everybody said, what's that? It was Danzig that made it useful. In other words, a model is fine, but until you can solve it, it's useless. Well, the 4 classes of policies is what makes my universal framework useful. So I had one slide with cloud to cloud lightning, and then I had another slide with a lightning bolt. And if you look at the front cover of my book, it's a front cover of a lightning
exactly
bolt. And I have another picture where I have the lightning bolt, and I have application up in the I have theory up in the sky, and I have application down on the ground. But in between, I have modeling and computation. Modeling and computation is what bridges theory and application. So you can just do theory and never solve a problem, or you can have problems where you just hack around. But if you want to take the theory and solve the problem, you've got to do modeling and computation. In deterministic, the modeling has sort of been viewed as something that everybody sort of knows how to model it. It's not really true, but it's when you do sequential decision problems, stochastic optimization, the modeling is much harder. So I had the universal framework, and then I said I got my 4 classes of policies. Then I had my lightning bolt slide, and I remember this vividly up in Montreal. And somehow I've used my group at Montreal to test out vocabularies and languages, and so I've kind of had fun using them that because it's a very friendly community. I don't have to feel like I have to do some heavy technical work. And so I've had a lot of fun with that.
Glad to know about that. Michel and Theo were both here as guests. And it's very interesting to know that you have this very good connection with them. Well, Warren, thank you so much for this great conversation. It was fabulous. I learned a lot, I must confess, and I hope the listeners also they can learn a lot as I did. So thank you so much once again for being here.
It's fabulous having somebody like you who's so knowledgeable about the field. You know what questions to ask, but this is a great opportunity to get some of these thoughts out. So thank you very much for this.
You're just being very kind. But if you're interested in visiting Brazil one of these days, please consider just dropping a line or, you know.
We have a wonderful group of Brazilians. Our head analytics person, Juliana Nascimento, is Brazilian. Our head engineer, Eduardo Silva, is Brazilian. Our human resources manager is Brazilian.
Wow.
Yeah, no, we have quite a few Brazilians at the company.
Yeah, maybe you can open a branch here. Who knows?
So I tell you, Juliana gave me a talk in my workshop because she did operations planning at Kimberly-Clark, Brazil, in Brazil for 8 years, and the war stories she had of what it takes to do logistics in Brazil.
That's an entire another story, chapter, and let's that if we go into there, that's a lot to talk. Anyway, thank you so much, Warren. See you. Take care. Bye.
Thank you.